So welcome to the final talk of the semester. We have Shyamal Patel from Columbia University. He's a final year PhD student, advised by Cliff Stein and Shi Chen. And he's going to start at UT Austin for a postdoc soon. And Shyamal's been doing really nice work in sublinear algorithms and um, other cool stuff. So we are excited to have him talk about learning functions of half spaces today. And maybe just before I turn it down to Shyamal, feel free to suggest more talks and even survey talks to TCS Plus, which is a online virtual seminar series using the Google form in our website. Shyamal, take it away.
Great, thanks. So I'm Shyamal, and I'm going to talk about learning functions of half spaces, and this is joint work with Josh Alman and Rocco Servedio. Great, so let's go ahead and get started by talking about the model of learning that we're going to be working in. And this is going to be the probably approximately correct learning model, which was introduced by Valiant and is one of the foundational models in computational learning theory. And in this model, there's going to be a hidden function f that's going to be Boolean valued, and it's going to be promised to come from some nice class of functions. So you should think of this as just being your favorite class. Maybe that's decision trees, half spaces, small circuits. There's also going to be a hidden distribution over the Boolean cube, so over the inputs. And the way that this model is going to work is that you're going to have a learning algorithm, which is input is going to get a bunch of labeled examples. So these examples are going to be drawn independently from the distribution D and labeled according to the hidden function f. These then are going to get fed into the learning algorithm, whose goal is to output a hypothesis. And you would like it to be the case that with high probability over the random examples, we have that the hypothesis that's output differs from the function on a small percentage, only let's say 1% of the inputs as drawn from the distribution, right? So this is where the name comes from. We want it to be probably approximately correct. Good. So this is the model that we're going to work in. Sometimes we'll also think of the domain as being Rn. In particular, the results for this talk are going to mostly also work for Rn. But it'll often be convenient to also talk about the cube. Great. So the main object of study that we're going to talk about are going to be half spaces. So these are going to be functions of the form sine of w dot x, where w is just some vector in Rn, and x is again, also lives in Rn. It's from the Boolean cube in n dimensions. And geometrically, you can think of this as being a hyperplane, and everything above it is labeled positively, and everything below it is labeled negatively. Now, it's worth noting that I'm assuming that there's no offset to this hyperplane right now, that it goes through the origin. It turns out that in the fully general pack model, where we don't make any assumptions about the distribution, this is going to be without loss of generality. So essentially, you can always reduce from the case where there's some constant term here that prevents it from going to the origin. It's w dot x, let's say minus theta would be the general form. You can always reduce to this origin-centered case in this setting. And so throughout the talk, I'm going to assume that our half spaces are origin-centered. Now, we've long known that half spaces are efficiently learnable in the pack model. And essentially, the way that this works is you just apply VC dimension arguments to say that if you were able to find a half space that correctly labels a set of, let's say, 10 endpoints, then you would get a hypothesis with good accuracy. And finding a half space that correctly labels a set of points turns out to just boil down to some linear programming. In particular, if I give you some examples and I tell you that, let's say, f of 1, 0, 1, 1 is positively labeled, then this will tell me that, if I look at the weights, the unknown weight vectors, that I need to have w1 plus w3 plus w4 is positive. Similarly, if I tell you that, f of 1, 0, 0, 0 is negative, this tells me that some other sum, in this case just w1, is negative. And at the end of the day, I'm just going to have roughly a linear number of inequalities, and I can just use, say, the ellipsoid algorithm to efficiently find a point in this polytope. Great. So we've long known that we can learn half spaces, and it's been of interest in the learning community to learn more general functions of half spaces. So in particular, some concept classes that we'd like to be able to learn that are sort of a little bit higher up in the hierarchy here are things like polytopes. You can think of a point lying in the polytope as being equivalent to saying that lies above all of the supporting hyperplanes that define the polytope. So in some sense, this is an intersection of half spaces, which I'll define for you a little more formally in a second. And then another class is just going to be, basic neural networks. So, a neural network, if you think of it sort of the simplest neural network, it has a linear function with a nonlinear activation. If you make this nonlinear activation the sine function, then this is exactly going to be a half space. And this is again going to correspond to a more complicated function of half spaces. So we'd like to be able to learn these things. And what do we know in the setting? So maybe the easiest question that we could ask here is if we can learn an intersection of two half spaces. So this is just going to be, there's two hyperplanes, W1 and W2, and a point is going to be labeled positively if it lies above both of them, and negatively otherwise. Now, unfortunately, for this concept class, we actually don't know of any non-trivial algorithms to learn it, at least in the general distribution setting. And maybe even more unsatisfying, as we'll see a little bit in a second, we actually don't have non-trivial learning we don't have any non-trivial lower bounds as well. So we know that information theoretically, if you did not care about the runtime of your algorithm, how long it takes to output the hypothesis, you'd only need a linear number of samples in order to solve this problem. You could output a hypothesis if you had unbounded runtime. On the other hand, the only upper bound we have is sort of the trivial upper bound, which is just saying that my points are coming from the Boolean cube. So I can just memorize the labels on all 2 to the n points and output this as my hypothesis. Good. So this is a pretty well-studied question, and we do know a lot about it. In particular, in a variety of restricted settings, we actually do have a good understanding of this question. So if you promise me that rather than being an arbitrary distribution, if you tell me that the distribution is nice, so let's say uniform over the unit sphere, log-concave, Gaussian, there's another so-called factorizable distributions. In all of these cases, it turns out that there's polynomial time algorithms for learning an intersection of two half spaces. Another assumption that people make in order to make the problem more tractable is that the half spaces are nice in some way. So if they have low integer weights, for instance, or equivalently, this works only over the Boolean cube setting, but if you want to think more geometrically, the requirement that they need is that no point lies too close to one of these hyperplanes. So all the points are sort of very much in the interior of these regions. Good. And in this case, you can get a quasi-polynomial time algorithm. So finally, we have algorithms in the case where you can ask for the labels of arbitrary points. So if you can query a point x and get back the value of the hidden function on that point x, we again know that you can solve this in polynomial time. Now, I'd like to motivate sort of the general distribution free setting here by saying that, for one thing, it's interesting to know what we can say without making any restrictions on the distribution. Also, maybe I'll say that for each of these settings, there's some drawbacks that it would be nice to get around. So for instance, for these nice distributions, almost by their very nature, they kind of tell us, well, they're interesting distributions under which to study the problem. They don't tell us a lot about learning in the presence of outliers or strong correlations, more or less by virtue of being so nice. In the cases where the half spaces are nice, where no point lies too close to the boundary, I think this is a pretty a reasonable assumption for the most part. But unfortunately, these algorithms turn out to be quite brittle. They very much require that no point is too close to the boundary. So even for distributions like the Gaussian, if you try to apply these algorithms, they break down because the Gaussian puts some amount of mass reasonably close to these hyperplanes. And these algorithms cannot handle that. For the last class, asking for the labels of arbitrary points, This is really a relatively strong power to give our algorithms the ability to have. So it's interesting to know what we can learn with random samples alone. And another qualm that people sometimes have with this model is that you can ask for the labels of maybe nonsensical points. So if maybe the analogy is if I give you a picture and I'm asking if it's a cat or a dog, or the picture looks like random noise, there's not really a sensible way to answer this question. Good. So as I mentioned, this question's been studied for a while now, and we don't have any upper bounds. So people have also thought a lot about hardness, and we have some evidence that this question might be hard. So in particular, some of the earliest evidence is that proper learning is NP complete. So what this means is that if the hypothesis that your learning algorithm outputs has to also be an intersection of two half spaces, this was later generalized to if it has to be the intersection of a few half spaces, so more than two, then in this case, this is going to be an NP complete problem. So you shouldn't expect to do this. But at the same time, if you're allowed to output a general hypothesis, this does not tell you anything about how difficult it is to do. And in particular, there's many other classes of reasonable hypotheses that you might want to learn with. So one class is maybe the sign of low degree polynomials. Maybe you'll take the intersection of these. So it's just a slight modification here. Another sort of nice class that seems relatively interpretable is threshold decision trees, which is it's just a standard decision tree, but each node has a corresponding half space, and whether you go left or right depends on the sign, how the half space labels that point. All this to say, there's just many other things you can output as hypotheses, so these don't really rule out efficient learning algorithms. Some other negative evidence is that there are, in fact, cryptographic and average case hardness assumptions, average case hardness of this problem, under assumptions like lattice cryptography and the hardness of things like Feige's conjecture for refuting K-SAT formulas. But here, they actually only prove that an intersection of K half spaces requires n to the omega of K time. So this rules out the possibility of learning, intersections of polynomially many half spaces in polynomial time. But for an intersection of two half spaces, these don't tell us anything interesting. Similarly, there's statistical query lower bounds. So these prove that, again, an intersection of K half spaces only require n to the omega of K time. And essentially, for those of you who aren't familiar, statistical query algorithms are a broad class of learning algorithms that contain almost all of the learning algorithms that we currently have, with the notable exception of Gaussian elimination. But again, for K equals 2, this isn't going to give us any sort of hardness. Finally, if you tell me that maybe the strongest evidence that we have that this problem is hard is a barrier against a very particular proof approach known as the polynomial method. So what is this method? It says that if you can take every function in your concept class, so for us, this is going to be if every intersection of two half spaces can be written as the sign of a low degree polynomial, then you can get an efficient learning algorithm. In particular, what you can do is you can take your point x and you can map it to the space of all degree at most d monomials. So there'll be a term here, not shown, for degree 1 monomials, so maybe x1. There'll be a term for x2. You'll have degree 2 monomials, x1 times x2, and then you'll have the degree d monomials shown here. Over this new feature space with these bigger vectors, we now have that the function is exactly a half space because I can take the coefficients of this polynomial as my vector, and this will correctly label the points. And because we can learn half spaces efficiently, I can roughly run this algorithm in the time that it takes to write down these vectors. So it takes me n to the O of d time in order to learn a class with this property. And in particular, in the distribution-free setting, when we don't make assumptions on the distribution, this yields a lot of the fastest algorithms. It either is the only way we know how to do it or recovers the same bounds for things like learning DNFs, learning decision trees, De Morgan formulas. But unfortunately, the work of Shurstov says that this will not work, at least naively, for an intersection of two half spaces. In particular, there exists two half spaces whose intersection requires a degree omega of n polynomial in order to represent it in this way. As such, we shouldn't expect to beat the naive 2 to the n time algorithm using this approach. So at this point, the question is there something to learn here, or is this class sort of beyond what we should hope to be able to, maybe extract some structure from and get a learning algorithm? And the main result that I want to talk about is that we can indeed learn something here. In particular, an intersection of two half spaces can be learned in 2 to the square root n time. Moreover, we can show a generalization of this to say that any function of roughly logarithmically many half spaces can be learned in 2 to the n to the 0.51 time. So maybe some instantiations. The second thing is intersections of log n half spaces are learnable in this time. And it also gives us a result for learning a non-trivial class of neural networks, namely those with log n layers in their first hidden, log n nodes in their first hidden layer. Great. So maybe before continuing, I just want to give you a roadmap for where we're headed for the rest of the talk. So I'm going to start by just talking about how to learn a single half space using a maybe non-linear programming approach, just to introduce some tools that we're going to use, as well as give some intuition for maybe some of the hardness for learning an intersection of two half spaces. Then we're going to move on to discuss how we can learn an intersection of two half spaces. We'll generalize that to 3 half spaces afterwards. And finally, I'll give you some broad strokes for how to handle k half spaces. Great. So let's go ahead and get started with just a single half space. So recall this is just a function of the form sine of w at x. And throughout the talk, I'm going to assume that the weight vector and all the points in our distribution lie on the unit sphere. Notably, this is without loss of generality because I can rescale the points without changing this sine function. And I will say that the one exception to assuming that the points lie on the unit sphere is when I'm drawing pictures. I only have 2, sometimes 3 dimensions to draw in, and the sphere kind of will cost me one of those, which is not so great. But anyways, what's the difficult case for learning a single half space? If you want to learn using something like a polynomial, or you want to learn with something like the perceptron algorithm, the hard case turns out to be when all the points really hug the hyperplane. In this case, there's not really a huge geometric difference between points that are above the hyperplane and those that are below it. You could just take this point and slightly perturb it to move it to the other side, and all of a sudden, its label has flipped, and a lot of these methods for polynomials and perceptron and things like this are not going to be very robust to these things. But in this case, it turns out that we can still learn, because if all the points are very much hugging a hyperplane, we can more or less recover this hyperplane, or at least determine some structural information about the points. In particular, they're very flat looking, right? In some direction, they have very low variance. And so because of this, we can sort of rescale the points, it turns out, to get a set of points that doesn't have this property. So this was the existence of such a transformation was first shown by Barth and Forster. An algorithmic variance that will be suitable for our purposes were then shown by Dunnigan and Mpala and Diakonikoulos et al. And essentially what they say is that if you give me any point set, you can transform it into a new point set on the sphere, such that at least a 1 over n fraction have a reasonable margin, a 1 over square root n margin. So what's a margin here? The margin of a point is just the distance it has to the hyperplane. And so I'm promising you that a reasonable fraction of points don't hug the hyperplane after I apply this transformation. And notably, as observed by Blum et al. When studying learning half spaces and with random classification noise, this is enough to learn a single half space. So things like the perceptron algorithm will work. But maybe just to illustrate another point, to introduce a couple extra tools that we'll use, is that we can also maybe directly show something like this by just noting that if we go ahead and look at the expectation over the data set of the function times w dot x, this needs to be reasonably large, I claim. So recall the function is just the sine of w dot x. So this is just the absolute value of w dot x. So it's clearly always positive. And some points need to contribute a large amount, because I'm promising you that at least 1 over n points contribute 1 over root n here. So this needs to be reasonably big. And by an averaging argument, this means that there simply must be some coordinate itself that has a large correlation with the function. Large meaning inverse polynomial. So maybe not so large, but reasonably large. And geometrically, what's really happening here is we're saying that if we look at the positive points, their mean and the negative points in their mean, these need to be reasonably separated, right? This is just a consequence of the fact that some points are reasonably far away from this hyperplane. And so, as such, there must be some coordinate that essentially testifies to this. Now, it turns out that if you can give me a function that's slightly correlated, you can boost this to learn to a higher accuracy, so 99%, which is what we wanted. Particularly these results of Shapira and Freund that say that if you can do slightly better than random, 1/2 plus gamma, then I can call this algorithm 1 over gamma squared times and learn to high accuracy. So in particular, I'll call this procedure roughly a polynomial many times and get an algorithm to learn half spaces in this way. Great. Does that make sense? Okay. So now I'm going to go ahead and move on to learning an intersection of two half spaces. And to start off, I just want to sort of give an instance to maybe think about here. So the hard case is going to be when every point comes with a twin. So we have these positive points here, and I'm going to form a negative point by just making a copy of it and slightly shifting it to the other side of the hyperplane. Moreover, every point is going to hug some hyperplane, right? So maybe it'll hug only one of them, or it could hug both of them, but they'll all hug at least one. And now, good. The radial isotropy theorems now aren't going to save us because we actually do have a reasonable fraction of points that might be far away from the hyperplane, right? So we're not quite going to be saved here. And sort of the difficulty is that in this case, to a lot of these geometric methods that I was talking about, perceptron, polynomials, these positive and negative examples are going to behave pretty identically, right? We're not going to really be able to distinguish this very small perturbation here. On the other hand, things like linear programming that worked also are all going to break down because when a point is negative, we don't know whether it's negative because of the label according to W2 or the label according to W1. For this reason, we can't just set up a linear program and have things work out. And maybe we can also view the hardness of proper learning as sort of saying that there's not really an easy fix to this type of thing. Good. So our main approach is that, yes, these blue points and red points are indistinguishable from one another, but they really come in three clusters. There are the points that are far from W1, those that are far from W2, and those that are maybe close to both. And notably, we can distinguish between these three clusters. And why is it useful to distinguish between these three clusters? Suppose that I could find a region that just contained points from this first cluster over here, right? So it only has the points where W1.x are reasonably big, and it doesn't contain any of the other points. In this case, these points are actually going to exactly be labeled according to W2, because W1 is always positive, right? So I could actually learn to classify these points correctly by simply sampling, n points and learning a half space that separates them. Then I could go ahead and, if a point is not in R, I don't know how it should be labeled. Maybe I'll flip a coin. But if a point is in this region R, I can label it according to this half space, and I'll do slightly better than random, assuming that this region R is non-trivially large, right? Good. Now, if we think about what I just said, we don't really need that these points all have very large inner product with W1. It in fact suffices that we just find a region where the points are in fact just positively labeled by W1, because that was all we really needed for these points to be labeled by W2, right? Good. So it turns out that this is actually also going to be a little bit too hard for us to do. Some of these points are going to slip through. Like this red point is going to unfortunately slip through our ability to find this region. But we can tolerate, it turns out, a small number of these points coming through. In particular, if a little of 1 over n fraction of points come into this region, I claim that we're still okay. Because when we go to learn our half space, we're going to go ahead and sample n points. And because there's only a little of 1 over n fraction of points that are bad, I don't expect to sample any of those. And so I should still be able to learn this half space here for W2 that will correctly classify these points in this region R. Good. So hopefully the high-level approach makes sense. So now we're going to go ahead and see how to accomplish this goal. And I claim that in order to do so, we're essentially going to have an unlabeled problem. Now, why is this going to be unlabeled? I claim that at this point, because I don't have a good way of distinguishing these labels from being random, they may as well be coin tosses. And for that reason, I'm just going to throw away the labels. And this is going to be not a crazy thing to do because I didn't know really how to make sense of them anyways. So the unlabeled problem that I have is that I have a bunch of points in Rn and some vector w, and I'm promised that at least a reasonable fraction, a 1 over n fraction, satisfy w dot x is at least 1 over root n. This will be by applying these like radial isotropy types of theorems, which I guess I forgot to mention earlier, but I'm going to apply them pretty much all the time and always assume that I have an assumption like this that holds. Good. Now, our goal is then to compute a region where w dot x is positive for almost all points in the region, right? That's what we wanted to do to get our learning algorithm. Now, there's an obvious obstacle here, which is that there's no labels, so we really have no information about w. So we're not going to be able to do this. So we're going to need to relax this a little bit. In particular, we're not going to force ourselves to learn one region, but we want to compute a set of not too many regions, such that there exists one of them, such that our half space is positive for almost all points in this region. Moreover, recall that we're actually going to need that this region contains a non-trivial fraction of points, because we're only going to get the points in this region correct, and we want to have a reasonably large advantage in order for the boosting arguments to not take too long. Now, what do I mean by not too many and non-trivial fraction here? If we want to run in 2 to the root n time, I want to compute a set of 2 to the root n regions, such that the regions contain a 2 to the minus square root n fraction of points. Okay, so how am I going to do this? Maybe the most naive way of doing it would be by sampling a random vector g, which is going to come from the sphere, and hope that it has high correlation with w. How high of correlation are we going to be able to get? We'll get something like n to the minus 1/4 if we want our runtime to be, if we want to have 2 to the root n regions, right? Okay, so this is a reasonably large correlation, much better than random, but it's not so big. And in particular, just because you're labeled positively by G, by no means indicates that you're going to be labeled positively by W. Maybe in this picture, most of the points, in fact, on the positive side are labeled negatively by W, despite G having large inner product with W, right? And the key insight is actually going to be that this is true, but if you actually tell me that G dot X is very large, then I actually expect the points in this region to have a non-trivial, to be labeled positively by W. So if I take this line and I just shift it very far up, I now do expect this property to be true. Good. So I'm going to commit a little bit of treason here and show a small calculation, just kind of a back of the napkin type of thing. Just because to sort of give an intuition for why such a statement should be true. Good. So we're going to want the correlation with W or a vector to be roughly n to the minus 1/4 times some logarithmic factor. And we're going to look at the region, as I said, of points that have large inner product with G, at least this n to the minus 1/4 type of quantity, right? And now, okay, instead of working with the sphere, I'm going to just work with a Gaussian distribution that's suitably normalized. So I expect it to have unit length, just because it'll be a little bit more convenient here. And what's the probability that a point lies in the region? Well, okay, I expect the variance to be about 1 over n, because it's a unit vector x, and so its variance should be 1 over n. And now, the chance that you lie in the region, you have to be at least alpha. And notably, this isn't going to be a mean zero variable, so we're going to have to subtract off the mean. And in particular, there's going to be a contribution from the mean from the component along the direction of w, right? This is the component where g is not actually distributed according to a Gaussian, because we're conditioning on this event here. So what's the component of the inner product that comes between g and x that comes from w? Well, it's just going to be w dot x times g dot w, which sort of by tail bounds, I expect it to be roughly equal to alpha, just by concentration. Okay, so now I'm just going to go ahead and massage this a little bit. So I'll bring this n up top. I'll pull this alpha out of the square. And I'm going to go ahead and, actually square this 1 minus wx term and drop the lower order term of w dot x. The calculations maybe not so important, but the takeaway here is that we end up getting something like this for the probability that you lie in the region. It's n to the minus square root n times n to the 2 root n times w dot x. And I claim that we like this quantity. It's a nice quantity because if w dot x is negative, then this quantity is going to be at most n to the minus root n. But if w dot x is at least 1 over root n, then this quantity is going to be, this second term is going to contribute at least n squared, right? Because the root n's will cancel, and I'll have an n squared. So in particular, the takeaway here is that points with a large positive margin are n squared times more likely to appear in the region than points that are negatively labeled by the half space. And for that reason, I expect, maybe there's 1 over n fraction of points that have a large margin, and then I expect, but they appear with n squared times as much likelihood. So I expect only a 1 over n fraction to be labeled negatively, right? So most points in this region are in fact positively labeled. So I've accomplished my goal. Moreover, I'll have that this region will contain a non-trivial fraction of points because there should be a reasonable fraction that are positively labeled by the half space, and these will all appear with probability at least n to the minus square root n. So I'll get this second condition as well. Good. So hopefully that makes sense for just some rough intuition for why this holds. And now, maybe I just want to take a step back and recast this a little bit and also just put everything together to see what the learning algorithm ends up being. So our learning algorithm ends up doing the following. It's going to make a bunch of guesses, and most of these are going to be garbage. They're not going to be correlated to W1. But for each guess, I'm going to go ahead and form the region that we talked about and run the algorithm that we were discussing before. But only for a guess that actually has a good inner product with W1 will this maybe do anything meaningful. And notably, when I do look at this guess, I'll have that these points are positively labeled by W1. So then when I sample my endpoints in this next step to learn a half space, this half space will correctly classify most points in this region R. And so I can form a good hypothesis by flipping a coin outside of R and labeling points in here according to R of X. Its advantage, as we discussed, will be outside of R, I get nothing. Inside of R, I get everything correct. So I expect to do better than random by roughly the size of R, which is a 2 to the minus root n fraction. And so I can use a boosting result, which will require me to call this algorithm roughly 2 to the root n times. Each call will take 2 to the root n time. And so I'll end up with an algorithm that runs in 2 to the root n time as promised. Does this make sense? Good. Okay, so I'll go ahead and talk about 3 half spaces now then. And notably, this framework of sort of making guesses is going to come up a lot. But anyways, for 3 half spaces, we're going to again sort of picture the same scenario here, where every point comes with sort of a twin of sorts. They all hug a hyperplane, and they come with this twin. Now, I would like to, I've shown one tool, and I want to get as much juice out of it as possible. So let's just try and use it again. So I'm going to go ahead and compute a region for, let's say, this first half space, W1, with the property that the fraction of points that are labeled, let's say, negatively is small, right? So this is going to be a 1 over n fraction of this total region, of this overall region. And now I want to restrict my attention to just the points in this region, right? In some case, I'd like to think that I've reduced to the problem to that of learning an intersection of 2 half spaces, right? And I just told you how to do that. So let's go ahead and do that. This requires us to, make a new guess G2 to try and form a new region, R2. And the hope is that in this region, R2, sort of by the arguments before, we know that W2 is going to be, the second half space is going to be always positive, except for a small fraction of points. And so I'd like it to be the case that these points also, because they're in R1, have it that there are few negatively labeled points according to the first half space as well, right? So almost all points in this region are labeled positively by both the first half space and the second half space. If that were the case, then I'd be happy because they're just labeled according to the third half space. I can then sample endpoints as I did before and learn in the same way. Unfortunately, taking a closer look here, we're going to run into some issues. In particular, this second region is actually quite small. It has size, n to the minus root n roughly times the first region. And in particular, this error region here is looking quite big by comparison. And so we need to be worried about the fact that we might no longer fix this first half space. Where by fix, I mean, I'm going to say the half space is fixed if it's, almost always constant in the region. So region fixes a half space if the half space is, almost always constant on that region. So now, the first half space could be both positive and negative, and that would be a problem here. And in particular, we can see that this actually will happen. If we go back to our rough calculation of the probability of a point lying in our region, what happens is we could have that, points in the gray region have margin roughly 1 over square root n with respect to W2. So they'll appear with n to the minus root n times n squared, because the root n's will cancel, and I'll just be left with an n squared term. But maybe points in this red region have margin 1.5 over square root n, right? Then that would make them appear with probability n to the minus root n times n cubed, because, again, the root n's cancel, and I have 1.5 times 2 here. So these points will appear with n cubed times the probability, with sort of n times the probability as the points in the gray region. And that'll roughly cancel out this size effect, the fact that it's a smaller set of points, right? And so for this reason, we may have that, the second region, W1 is almost always positive, but W2 could be both positive and negative, and that's a problem for us. But I want to say that in this case, we actually have that W2 has a good fraction of points with a larger margin. In particular, before, these radial isotropy theorems only told us that we had a non-trivial fraction of points with margin 1 over root n. But now I'm telling you that actually there exists a non-trivial fraction of points that have margin 1.5 over root n, right? So I'm doing a little bit better. And I'd like to take advantage of that. And this is how we're going to learn 3 half spaces. So we're going to continue with the same approach that we did before. We have the half spaces for W1 and W2. And I'd like to find a region where both of them are constant. I want them both to be fixed. Now, how are we going to take advantage of the fact that the margins grew here? We're going to do a little bit of symmetry breaking. And in particular, we're going to choose our first guess to be 10 times bigger than it was before. So it needs to have 10 times larger correlation. Okay, and so now what's going to happen? Okay, so we can take our formula from before, and we get some extra constants up top. And now when the points that had margin 1 over root n with respect to W1 are going to be n to the 200 times more likely to lie in the region. So this area region is not going to be 1 over n smaller. It's actually going to be n to the minus 200 smaller. Just by virtue of the fact that we spent a little bit more effort in finding a good guess. Okay, so now we fixed the first half space, and we now need to fix the second one. To do so, we're actually going to take a normal guess without this constant overblow, the same as before. And if this fixes both half spaces, we would be done, right? So I'm going to assume that it has a big overlap with this negative region in order for us to continue here, right? And in this case, we can do the same computation as we did before. We can say that, if the points in the gray region have margin 1 over root n, then the points in the red region ought to have margin something like 100 over root n, because there's n to the minus 200 of them. And so I need this sort of advantage term over here to be like n to the 200. And so, I'll have the root n's cancel, and I need an 100 here to get an n to the 200 from this term. Okay, so right now I haven't done anything. I've just sort of spent more time making this first guess, and I'm getting better constants out of it. But the insight is now going to be, if we are in this scenario where these points actually have a non-trivial margin, I'm going to just essentially restart. So I'm still going to focus only on the points in R1, but I'm going to imagine taking a guess for W2 that was actually as good as W1. So it's going to be 10 times what it was before, this factor of 10 here. And why am I going to do this? How am I making progress? Well, in some sense, I'm losing progress because I'm no longer going to fix the first half space. It could be both positive and negative when I look at this region R2. But if I go ahead and look at the probability of a point lying in this region, it's going to be, given by this expression. And I now have that these points actually have very big margin. They have 100 over root n margin, right? So if I go over here, I can see that they'll appear with probability n to the 20,000 times that of those points labeled negatively. So I've made some progress. Namely, the error region here is going to be even smaller. And now, okay, I need to go back and try and fix the first half space. So I'm going to, again, imagine trying to do this by taking a weak guess, so without this factor of 10. If I was able to get a region where both half spaces are constant, I'm done. If not, then I know this region ought to have non-trivial overlap with both. Okay, so then what I'm going to do is I'm again going to just make the same observation that I was making before. And I'm going to say that maybe these points in R2, they have margin 1 over root n with respect to W1. Okay, but I know that these points, because they come from a set that's so much smaller, n to the minus 20,000, they actually need to have margin 10,000 over root n, right? Because again, this advantage term needs to compete with this n to the minus 20,000. And so I need this to be roughly 10,000 here. And so now these have to have even bigger margin. And so again, I'll sort of restart. I'll still only restrict my attention to the points in R2, but I'll take a bigger guess. And when I do so, I'll get that the error region is going to be even smaller. It'll be like n to the minus 2 million times the size of this region here. And if we keep doing this, by the kth iteration, either we will have seen a region where both half spaces were fixed, meaning it's constant, and then we can learn and we're done. Or the error region is sort of shrinking doubly exponentially, and the margin is sort of increasing exponentially of the bad points here. Okay, so now we just note that the points that we're working with come from the unit sphere. So they can't have distance more than 1 from any hyperplane. And so after log n iterations, this process has to end. And we must find a region where both of the hyperplanes, both half space 1 and 2, were fixed. Okay, so this is what we're going to use to learn an intersection of 3 half spaces. And now I just want to give maybe some broad strokes of generalizing decay half spaces. So here we have some arbitrary Boolean function, and we have k half spaces, and we just want to learn this. And our approach is going to be essentially the same thing that we've been doing here. We want to find a region where all of the hyperplanes, or all of the half spaces, are constant, or nearly constant, where they're all fixed. In particular, doing so, this will then just be a constant function over that region, and I can learn it very easily. And here's like a picture of Gaussian pancakes. These functions of half spaces can be quite crazy and learn kind of computationally difficult things, which is partially where some of these lower bounds for learning in things like intersections of half spaces come about. Great. So roughly the broad outline of how we're going to do this is we're going to have a leaderboard of half spaces. So similar to before, where we're using a really good guess for the first half space and a slightly worse guess for the second one, the first position on the leaderboard is going to get the best guess of them all. And the second one will get, a slightly worse guess. The third one on the leaderboard will get a slightly worse one after that. And notably, everything in the leaderboard is going to be currently constant in the region that we're looking at, or nearly constant, right? They'll all be fixed. Now we're going to come along with a new half space, and we're going to want to have to make this be constant. And doing so might ruin some of our progress. In particular, maybe these, when we restrict to the region that fixes half space 2, will ruin, like these two will no longer be constant, right? So we'll get an updated leaderboard with these two half spaces. And notably, we need to make progress in some way. We can't just have things keep knocking each other off willy-nilly. And we're going to make progress in a similar way that we were making before in the case of 3 half spaces. In particular, if half space 2 is going to replace half space 1 as the second position on the leaderboard, it ought to be the case that there's a reasonable fraction of points that have twice the margin that half space 1 had when it was fixed, right? So if we go back in time and when we fixed half space 1, if those points had margin like 10 over root n, then I need to have that there were points for half space 2 that had margin 20 over root n. Good. And so now what do the dynamics of this play out? How does this play out, like with this kind of potential function here? Essentially, we're going to have a bunch of half spaces, and initially everything is unfixed. Now, we're going to go along and compute our first region, and maybe that'll fix the first half space. Then maybe the second half space comes along, we'll fix that one. And maybe when we fixed it, it only had points at margin 1 over root n. Then the third half space comes along, fourth half space comes along. We fix all of these and they don't mess each other up. So we're doing really well so far. We just have one more half space to fix. But unfortunately, when we fix that one, maybe it unfixes everything else. But by virtue of doing so, it must have had points with twice the margin, right? Had to have double the 2 times n to the minus 1/2, right? Good. And so now, maybe we'll try and fix the first half space again, because now we need to sort of fix these. And so we'll continue this process. But again, when the last one comes in, maybe it'll replace the second slot. But again, if we did that, these now needed to go from having 1 over root n to 2 over root n. And so we're slowly going to make progress in this way. But note that we're essentially kind of going through all, if we think of this as being like a string, where this is with like k letters, and this is like the alphabet, we're essentially kind of going through all of these strings. How many strings are there? Well, there's roughly log n levels. And there's, k characters. And so we'll get something like log n to the O of k as an overhead in our runtime. And so our result will end up looking something like this. So maybe I'll just end now with a few future directions. So the first is, can we learn a function of polynomially many half spaces in sub-exponential time? So right now we're sort of paying this exponential overhead in doubly exponential in k overhead here. So it'd be interesting if you could make this, a polynomial in k or even perhaps linear. As far as I know, there's no barriers to doing this, so that'd be interesting. Another question is just sort of maybe more basic of just, is there a super polynomial lower bound, let's say in the SQ model or under cryptographic or average case assumptions for learning an intersection of two half spaces? Is this problem actually hard without any assumptions of the distribution? Another question that I guess seems interesting to me is, can we prove an n to the omega of k lower bound for an intersection of k half spaces? I think this is particularly interesting because for a lot of even nice distributions, things like log-concave distributions or learning intersections of half spaces over even the uniform distributions with query access to the function, these algorithms run in n to the k time. So this would at least also separate sort of learning under these nice distributions from learning under arbitrary distributions. Anyways, that's all I have. Thanks.
Thank you. Does anybody have any questions? We can also switch to the unrecorded session for questions later. But if you have any questions now, please feel free to ask. Right. I actually have a quick clarification question. So when you are restarting the guessing, you are starting from scratch, right? Like the region does not shrink. Like
Yeah, so we're not quite starting from scratch, but we are like I don't look at R2. I'll throw out this, I'll make a new region I'm only going to look at the points in region R1 here.
okay.
So like I'm not quite starting from scratch actually.
You're not okay. So but that doesn't shrink the regions too much though. Like
So each time I do this, the regions will shrink by like a 2 to the minus root n factor.
but that's okay.
But
Like,
that's okay because I guess I'm only
you're
going to
only
do
going to
this
do
log
log
n
n.
times.
Yeah,
Yeah.
okay. I see. Okay. Okay, it's because you're only doing log n times. Okay.
Yeah.
Cool. Thank you.
Yeah.
One more thing I wanted to ask was about the nice distribution assumptions. So all those results are not, so by nature it's not without loss of generality to think about bias zero. So but they do go through without bias zero as well. Like
Actually, yeah. So these turned out to be. It turns out that somehow for a lot of these distributions, actually putting them through the origin versus not through the origin for nice things like even Gaussian distributions turn out to behave very differently. So actually, you have to like people do a lot of work to try and,
Okay,
prove them in the general setting as opposed to the,
I see.
yeah.
Okay,
But
cool.
yeah, it's very much not free for them.
I see. Okay, cool. Thank you.
Mhm.
Does anybody have any questions?
Oh, yeah, I have a question.
Mhm.
Are you making any assumptions about the half spaces? For example, are the perpendicular vectors to the half spaces, are they linearly independent? Does it depend on?
No, they can be whatever you want. There's no assumptions on the half spaces here.
So they could even be in the same direction.
Yes. Yeah. In fact, I guess like for some of these hard cases, like these like Gaussian pancake types of things, they will be in the same direction, and that'll be the difficult case. Oh, wait, once I get there. There we go. Yeah. Like they very much like they're just kind of offset, or I guess they're slightly different directions actually when you do the reduction to origin centered. But yeah, it's totally fine for them to be in the same direction. There's no linear independence or anything.
Okay. So let me just turn off the recording in case anybody else wants to have a discussion off the record. Thank you.